So when we're studying these multivariable functions, so far when we've talked about derivatives, we've talked about partials. And so we said, well, if you hold y, for example, constant, we can find the partial with respect to x. Now, remember what that is. That's where we are finding the slope of a tangent that runs in the direction of x. So we hold y constant, and we're getting the slope of a tangent in the direction of x. In other words, it's above a line that's parallel to the x-axis. Likewise, the partial with respect to y, we're getting the slope of a tangent in what we say is the y direction, where you're holding x constant and you're getting the slope of a tangent that's above a line that's parallel to the y-axis. But there are other directions, right? There's other directions. So what we want to do today is look at what's called the directional derivative. And in fact, we're going to look at the slope of a tangent that's above a line just in any direction. Now, to start off with, I wanted to show you a picture of precisely what I'm talking about. We've got this surface here that's in blue, and it's labeled with an S. Okay, so we've got this surface, and you notice down here there's a vector. There is a vector down here labeled U, and it's on a line. You know, this line, it's in the direction of this line down here. And what we do is we have this starting point here. And we go up here until we hit the surface. And you notice there's a tangent up here. Okay? Now that tangent is above this line that is not parallel to the x-axis and is not parallel to the y-axis. It's in the direction of this vector down here, this unit vector, u. So it's in that direction, and what we're doing is we're getting the slope of the tangent for this line. Well, what we want to do is figure out how do we do that? Because it's easy for partials. But, and it's going to be easy to find directional derivatives too. It's just a matter of, you know, using a technique. Now, before we do that though, I want to look at a little bit of preliminary. I want to do just some background. And what I've done here is I've got a vector down here, and this vector is, you can see it here, it's 2, 1. Okay, so I've got a vector 2, 1 down there in the orange. And above it is the red line, and that red line is parallel to that vector, of course. Now, we know it's parallel because it has the same slope. So, for example, this vector up here, 2, 1, if we pick any point on here, like right there, and I go over 2 and up 1, over 2 and up 1, over 2 and up 1, I'm always back on that line. So we know they're parallel. Now, what I want to do is this. So I want to just pick a point here, this point here, which is 2, 3. So I've got a point on the line. And I want to make an observation. So here's what we know. We know if we go over 2 and up 1, we're going to be at a point on the line again. But let's look at this. Let's suppose we take this vector, and let's suppose we multiply by 3. So I'm going to take 3 times that vector. And of course, what I get is I get a 6 and I get a 3. That's what I get. Okay? Now, I'm going to take this original point, which is 2, and I'm going to do this. I'm going to add to it 3 times 2. In other words, what I'm doing is multiplying 3 times this 2 here, and I'm going to add that to the x, and then I'm going to take the 3 and add 3 times 1. And I get a new point. And I just picked 3 arbitrarily, 3 times the vector. But let's see what point I get here. I get, this is 6, 7, 8. So I get this point 8, and this is 6. So I get the point 8, 6. Now I'm going to plot that point and see where it lands me. I go 1, 2, 3, 4, 5, 6, 7, 8, and then up 6. 1, 2, 3, 4, 5, 6. Ah, look at that. I'm back on the line, which is no surprise, right? because we said this vector was parallel, and me multiplying by constant just gives me a parallel vector, another vector parallel. I mean, same thing. It just changes the magnitude. Now, let's think about this. So what I'm saying is this. If we have a point on this line, xy, and if I add some multiple of the x component, I'm going to get an x coordinate that's on this line. And if I do the same thing to the y, whoops, this should be a plus. Sorry about that. Should be a plus right here. Okay, a plus. And this one is going to be a plus. Okay? That point is on the line as well. So no matter what, if I just multiply the vector v by any s, I'm going to get a point that's on that line. There's no question about that. Okay, any questions about that idea? Now, what I want to do is I want to just, first of all, look at the length. I want to look at the distance from the original point to our new point. I want to just see what that distance is. Okay? So I'm going to use the distance formula. Here's the distance formula. The distance formula says I'm going to take the square root of the difference of the x's squared. I'm going to take the difference of the x's squared plus the difference of the y's squared. I'm going to take the square root of that, and let's see what I get. Well, it looks like what I'm going to get is s squared v1 squared plus s squared v2 squared. Now, s is a positive distance here. I'm going to say this. I'm going to say, let's assume that s is positive. And if s is positive, I could factor out that s squared, take the square root of it, and I get s times the square root of v1 squared plus v2 squared. Okay. Does everybody see that? In other words, the distance from xy to x plus SV1, y SV2 is s times this. Has anyone recognized this? What is that? Yeah, that's the magnitude of v. So here's what we have. We have s times the magnitude of v. So the distance from here to here is s times the magnitude of v. No question about it. Okay, now, so this is what we have. Now, so you can see that what I have is I have a line that's, we could say, okay, it's parallel to this vector v, and the distance is s. Now, we're getting close to talking about looking at the tangent above a line that's parallel to a given vector. That's where we're going with this. Now, you see that this right here is a little more complicated than we would like it to be. Why don't we do this? Why don't we say, well, instead of just talking about a parallel to a vector, let's say we're talking about a line parallel to a unit vector. Now, if we're talking about a line parallel to a unit vector, then that means that the distance from xy to this other point would be just s. And that would be nice. So let's do this. Let's say that we're going to use in our discussion a unit vector. And let's suppose, I'll just write it this way. Whoops, backwards. We're just going to say it's a unit vector. And in this case, it would be v over the magnitude of v. Okay? So that's what we're going to use. Okay? Any questions about that? So now we know the distance. Okay. Now we're ready to define what we mean by directional derivative. So let's suppose that we're on the plane and we want to know the slope of a tangent that corresponds to a surface above us. So here's what we want to do. We've got this point, xy, and we're looking up at the surface and we want to say, okay, there's a tangent up here. So we're going from xy a little further down this line to another point, and we're projecting up the plane so that it intersects the curve in the surface in a curve, and we're wanting to get the slope of the tangent to that curve at xy. Is everybody clear on what I'm talking about? So let me go a little further and do this. I'm going to say, okay, I've got this other point, x plus s u1 and y plus s u2. Now remember, the distance from xy to this point is s, because we're dealing with the unit vector. So let's talk about the tangent up there. Now remember, so here's what we've got. We've got this surface defined this way. You give me an x, you give me a y, and I'll give you a point on the surface. So let's talk about the derivative. So here we go. We're going to take a limit as s goes to 0. In other words, we're looking at this horizontal distance down here, or this distance on the xy plane. And up here, we're going to have f of x plus s u1, comma, y plus s u2 minus f of xy all over s. Does everybody see why that makes sense? We're looking at the slope of the tangent up there on that surface where this plane intersects, and we get a curve. Now, we refer to this as the directional derivative. Denote it this way. Capital D, and I have a little vector down here, and we're going to say f x y. There's the directional derivative. So that's the notation that we're going to use. This is the directional derivative in the direction of u of this function, right? Any questions about that? Okay. The directional derivative. Now, this is the definition of directional derivative, but it's very difficult to use this. I mean, in practice, it's just like in Cal 1, when we learned the definition of a derivative, we soon learned ways that we could have a shortcut, because we're not going to use this generally. But we always start off with the definition, and here's what we're going to find. We're going to find this, that this, the directional derivative in the direction of u can be written this way. It can be written the partial with respect to x times u1 plus the partial with respect to y times u2. This is what we're going to use a lot of times. Okay? So this is a big shortcut, and you can see how this would be easier. What we've got to do is prove that that's true. In other words, I've got to prove that these two things are the same. Okay? So that's what we want to do next. Okay, so let's do this. Let's just create a new function here. I'll call this g of s. Okay? So this is just a single variable function in terms of s, right? And I'm going to say that this function is defined to be x plus su1, y plus su2. Okay? So there is my single variable function. Now, I want to do this. Let's talk about the derivative. For example, let's just look at the derivative of s prime of 0. We'll just start off talking about the derivative of s prime of 0. Now, by definition, that's going to be the limit as s goes to 0. And up here, we're going to have g of s minus g of 0, right? And down here, we would have s minus 0. I'm kind of using the alternative definition of a derivative, right? It's just the change in the function values over the change in the independent variable values. But this right here is g prime of 0, isn't it? Now, if you look at this, so what is, if I replace everything up here, you would see that I get right back to the definition of the directional derivative, right? In other words, so we know that this g function here is the directional derivative because you can easily substitute back in and get that. Now, let's break away from that a little bit and then say this. Let's look at it, finding g prime of 0 a different way. Let's suppose that w equals g of s. And let's also make this, let's say this. Let's suppose that instead of f of xy, let's just say, or instead of f being this stuff, let's do this. Let's say that this is going to be p comma q, where p is equal to x plus s u1 and q is equal to y plus s u2. Let's just suppose that we have that. So this is just a trick because what I want to do is show that g prime of 0, which is clearly the definition of a directional derivative, I want to show that that's the same as the shortcut that I presented a minute ago. Does everyone see what I'm doing here? Now let's look at this. I'm going to take dw ds. Okay. In other words, I'm going to get the derivative with respect to s, and this is going to be like g prime of s. But if you look at this, if you look at this part of it, what's this going to be? Well, this is going to be the partial of w with respect to p times the derivative of p with respect to s, right? Y'all see that? In other words, I'm just using the chain rule. And I have to do a partial here because there's a p and the q. But here I don't need to do a partial. Does everybody see that? Okay. Now I'm going to do the other one. I'm going to do a partial w with respect to q, and then this is going to be dq ds. Is everybody with me on this? Okay, now I'm going to come back and look what I have here. What I have now is this, partial of w with respect to p. Well, this is f sub p, p, q. Now, what is the partial of p with respect to s? It's just u1, right? Do y'all see that? And what is the partial of w with respect to q? Well, it's going to be f sub q, pq, and then this is going to be u2. Ah, we're almost there. Look at what we have here. Now, what if I do this? This is g prime of s. Well, what if I say g prime of 0? Well, if you think about it then, this p becomes x, doesn't it? Okay? So here's what we've got. This is going to be f sub x, xy, u1. And what about this one over here, q? What does q become? Yeah, y. So this is xy, u2. Ah, there it is. Look at that. So look, we just said that g prime of 0, we showed that that is how we're defining the directional derivative. With that same function, we showed, yeah, g prime of 0 is also this, right? It's also that thing. So this thing is what we want to use. Does everybody see that? So we have the definition for directional derivative, and then we have this. Are there any questions about that at all? Okay, now, one more thing. Connected to this, we want to look at this thing. This cool thing right here. It's like an upside-down delta. And, you know, sometimes you hear this called del, D-E-L. I guess that's how you pronounce it, del. But it's an operator. It's an operator. It's a vector differential operator. And it's written this way. You have an I. And really, up until this point, you haven't dealt much with operators and the whole language and the use of operators. But what this does is, when it's applied to a function, what it's going to do is it's going to take the partial with respect to x. It's going to take that part of the function and put an I on it, and then the partial with respect to y and put a j on it. So what this does is it turns a function into a vector. So here's what's going to happen. We're going to take this. We're going to take this little thing here and connect it to this function. In other words, this vector differential operator is going to act on this function. And here's what you're going to get. You're going to get, let me go ahead and write it out here, I like that. And this right here is called the gradient. Gradient. Okay, so that is the gradient. Now, when you see this, if you think about this and you realize this, we said that the directional derivative is equal to this. The directional derivative, recall, is equal to, and let me just do some shortcuts here, or shorthand. Didn't we say that that was what the directional derivative was? We said that. Now, what if we do this? What if I take this thing, the gradient? Let's suppose I take the gradient, and okay, so does everybody agree that's the gradient? Okay, and what if I dot product that with this vector right here, u1, u2? In other words, this is the vector that our directional derivative, we're using this vector to talk about the direction of our directional derivative, right? So this is the unit vector. So what if I do this? What if I take the gradient and dot product it with that vector? Well, then look what we get. We get So it looks like what we have here, and notice that this is the same as that. So it looks like we have another way to view, or another way to talk about a directional derivative. We can say this: it's going to be the gradient dotted with the direction. So that right there, whoops, let me, since it's a unit vector, let me go ahead and use this. And we said that that is the directional derivative. Okay? Any questions about that? So that's something we can now talk about. Any questions at all about that? So the gradient's pretty simple. And we can use the gradient to talk about directional derivative. Okay. Okay. Now, one of the things I want to point out about the gradient that's very important is going to require us to hearken back to think about the angle between two vectors. Remember, if we have two vectors, and I'll call maybe a vector A and B. So these are vectors, two vectors. And remember we said before, if we want the angle between those two vectors, we might say this. We might say, okay, the angle is going to be cosine beta. Let's say beta is the angle between those two vectors. It's equal to the dot product of those vectors. Whoops, look at me. This is not necessarily a unit vector here. I don't know what I'm doing. And I did it here too. Let's suppose, okay, so we've got A dot B, and it's over the magnitude of A, magnitude of B. Okay, so this is the angle between two vectors. We remember that. Now, we also use this to talk about an alternative way of looking at the dot product. So we could say, well, the dot product of AB is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the vectors. This is something that we looked at before, right? Okay, now, with that in mind, you can see that anytime we have the dot product, we can rewrite it this way. Okay, so let's do that. Let's play around with that. And let's look at this dot product. Let's suppose that we've got the gradient of f, and we dot that with the unit vector u. Okay, let's just suppose that we make that dot product. Okay, and let's see what we get. That's of course a dot product. Well, we know that we can write that as the magnitude of f, the gradient, times the magnitude of u, times cosine of beta. Now, can that be simplified at all? Can I take anything out? Yeah, the magnitude of the unit vector, we can easily take that out. So now we have cosine of beta. Look at this. Now let's think about what this implies here. Remember, the directional derivative, it measures change, right? So it's a rate of change. And let's see what we've got here. We've really got this. We've got that the directional derivative in the direction of u, because that's what this is equal to the magnitude of the gradient cosine beta. Now, so I'm going to ask this. What is the biggest value that the directional derivative of f can have? Or the directional derivative in the direction of u can have? What is the big? Yeah, the magnitude of the gradient. Well, that's pretty interesting, right? Because we're saying that if you want to talk about the direction of the greatest change, then or the greatest increase, that's going to be in the direction of, or the greatest change possible is going to be the magnitude of the gradient, right? Now, the direction then also would then be the magnitude of f, right? So we're talking about, so let's suppose, let's look at this next slide. Let's suppose we're standing down here on this green plane, which is the xy axis. And we're looking up at this surface, and we're wondering, okay, which direction should I go, these red arrows, so that if I were to go up and go that direction on the surface, where would it be the steepest? Well, in other words, if you project up here, let me see if I can do a decent job of projecting up. There's that, and you're going that way. You're wondering, okay, which direction would be the steepest? What is the steepest climb on this thing? Well, what we've just shown is the steepest climb is going to be in the direction of the gradient. So you say, okay, which one of these arrows is the gradient? I go that way, and that's going to be the steepest climb up this surface. Okay? And the steepness is the magnitude, right? That's the rate of change. That's the greatest rate of change, and the greatest rate of change occurs in that direction. Y'all dig what I'm saying? Okay? So you're taking the steepest route. Now, think about this. If that's the steepest route, what would be the route of greatest decrease? Huh? Yeah, it would be in the opposite direction, right? In other words, look at cosine beta. Cosine could be 1, right? Yeah, the greatest decrease. The greatest decrease. Well, if cosine beta could be 1, it could be 1. And that's when the angle, so look, maybe I didn't specify this as clearly as I should have. Cosine beta is 1 whenever beta is 0, right? Okay. That means the angle between these vectors, the gradient, the angle between these vectors right here is 0. That means you're in the direction, right, of the gradient. So look, so the gradient is the direction of the steepest increase, the greatest increase, and also it's, the magnitude is the greatest increase, right? Do y'all see that? Now, if you want to talk about the opposite, you would say, well, when beta is equal to pi, right? Pi. So it's the opposite way, right? So if you want to talk about, well, what is the direction of the greatest decrease? Well, it would be negative this, right? And the actual decrease, the value of it would be the magnitude of the negative magnitude. Okay, does everybody see that? So this is where you decrease the most, and this is the most decrease, right? In other words, this is the smallest that can be, the gradient. Any questions? Any questions about any of this discussion?